Dear ladies and gentlemen, today I would like to present to you the results of my research on the topic Peridynamic modeling of dynamic crack initiation. In this work, the problem of dynamic crack initiation in the brittle solid body was studied using the non-classical approaches of continuum mechanics, peridynamics, and structure-time approach of fracture mechanics. In the end of the last century, Ravichandra and Knaus conducted a series of experiments on the dynamic crack initiation, its propagation and crack arrest in the brittle samples made of a glassy polymer material, Hamlite 100. In their experiments on initiation of the crack growth, trapezoidal pressure pulses of the various amplitudes were applied to the crack surfaces with a very short growth duration of 25 microseconds. Depending on the amplitude of the applied loads, the time after which the crack growth started varied. The higher the amplitude, the earlier the crack growth was initiated. Measured values of the stress intensity factor at the moment of crack initiation, when the time of fracture is small, for Hamlite it's less than 50 microseconds, showed a strong difference from the critical stress intensity factor measured during the quasi-static tests. That of course contradicts to the classical Griffiths-Irwin approach. In view of the dynamic dependence of the stress intensity factor on the time to fracture, it would be very important to simulate described experiment using developed to date innovative approaches of solid mechanics. In the present work, peridynamic approach was used to study the problem of dynamic crack initiation. A well-known state-based ordinary material model was used. Peridynamic simulations were conducted in the open-sourced software Peridynamic, which is developed by Sandia National Laboratories. As it was already mentioned, the classical approach is not able to describe the effect of dynamic crack initiation. So, in this work, a different approach was used, the structure-time fracture criterion. An idea of the structural criterion is that there is a parameter such as a characteristic length. The crack propagation is a failure of the structural blocks of size d, one after another, starting from the crack tip. This approach states that there is a process zone of fracture opposed to the classical approach, which rejects it. So, the criterion states that the structural block of size d will fail if the average stress of this block exceeds the critical tensile stress of material sigma c. Average stress value is determined through the integral as it's shown on the slide. Structural size d is determined from condition of the correspondence of the structural criterion to the classical approach within the framework of linear elastic fracture mechanics, and this parameter is a material constant. The formula for determining this parameter you can find on the slide, where K1C is a quasi-static critical stress intensity factor of the material. Structure-time criterion is an extension of the structural criterion, and it considers the mean value of the stress variations both in the space over the structural block of size d and over the time of duration tau. Tau is an incubation time, which is a characteristic time of fracture. It's supposed that fracture is not an instantaneous process, but on the contrary, material needs a time to prepare for it. This parameter can be found using an analytical approximation to the experimental results, and it's a material constant as well. In order to implement structural approach in peridynamics, a separate failure of the bonds is considered, as for the classical failure criteria in peridynamics. Since this approach considers the stress field, it's necessary to introduce the concept of the bond stress, which in this work is assumed to be equal to the mean value of the stresses in the interacting elements, as some other authors have already done. By sigma, any component of the stress tensor is meant. For example, stress component of the bond sigma 11 is equal to the sum of sigma 11 in the first particle and sigma 11 in the second particle divided by 2. The failure of a structural block is interpreted as the failure of all bonds of the peridynamic particle occupying a volume in the form of a cube with an edge of size d. If we consider the case when a critical stress is reached in the considered peridynamic particle and its neighboring particle has even a zero stress value, then the connection between them has to fail. Therefore, we obtain that the critical bond stress is equal to a half of the quasi-static strength of material sigma c. Due to the heterogeneity of the stress field at the crack tip, the average stress value on a structural block strongly depends on its size. In case of the inverse root asymptotic approximation of the stress field, it's easy to find out that the average stress on a structural element of the size k times d is square of k times less than on the structural block of size d. Consequently, the critical of the average stress on a structural block of size k times d as well must be square of k times less. This feature allows to use this criterion for any element size that's very important for its numerical implementation, especially in peridynamic numerical approaches, which are computationally expensive for the element size of d. For example, for homolyte 100, parameter d is only 0.064 mm. Considering all mentioned above, the structure-time criterion of the bond failure will be formulated in the following form. Bond has to fail when the average stress value on the element size of k times d over incubation time tau is more or equal than a critical tensile stress of material sigma c divided by 2 times square of k. Only normal stresses are taken into consideration. In order to calculate an average bond stress value over the incubation time tau, a stress time history of each element is stored over the previous n time steps. Calculation time step is selected so that it's a multiple of the incubation time. Then, using a trapezoidal rule, time histories of the bond stresses on each area are integrated and a maximum positive value over all areas is compared with the critical value. In the present work, crack initiation tests were modeled in the similar manner as it was done in the experiments of Ravichandra and Naus. For this study, homolyte 100 specimen with sizes of 250 mm in height, 150 mm wide, 3 mm in thickness with a pre-notch length of 25 mm was found to be inappropriate, as the reflected waves from the boundaries don't reach a correct tip during 80 microseconds. Discretization size was taken 0.5 mm and horizon size was taken 3 times greater than a discretization size. The first boundary conditions were applied to the portion of the crack surfaces in the width of 2 horizons, leaving the near-tip fracture surfaces free for the J integral calculation. Stress intensity factor was calculated using dynamic J integral approach, drawing a contour around the current location of the crack tip, so that only neighborhood of the particle located at the crack tip is placed inside the contour of J integral. Crack initiation was considered at the moment when in the next element after the crack tip the damage of at least 35% was achieved. As a result, dependence of the stress intensity factor on time to fracture was obtained, and it adequately predicts the experimental dependence when tau is equal to 9 microseconds. Additionally, results for the different values of tau were obtained. Also, we can find transition of obtained dependence to the quasi-static critical stress intensity value that demonstrates independence of incubation time criterion on significance of the inertial effects that is a crucial feature of this approach. This result was already obtained analytically for the structural time fracture model, but it's of the main importance that the same result was obtained using the fracture model in conjunction with peridynamics. Thank you very much for your attention.